Hello everybody, this is Shane Hale here at the GC factory here in Houston. Thank you for joining us this morning or this afternoon, depending on where you are. We're going to be talking about communicating with your gas chromatograph using Modbus with RS-232, 485 and Ethernet. I do have a poll up at the moment, so if you would, while we wait to begin the main section of the presentation, if you can go to the poll and answer that question there. The main question I have there is, what's the main way you communicate to your GCs today? RS-232, 485, 422, Ethernet, wired or fiber optic, or foundation field bus? And I'm just peeking at the results there. We'll go over the results in a minute, but I see that we've got quite a few people that have answered already, and Ethernet is actually coming out ahead, which is interesting and good news, but obviously 232 and 485 are there as well. So during this presentation, we'll go through the details of 232, 485, and 422 and Ethernet, and talk about all the different ways to communicate. So we'll just wait 1 minute while we get a few more people coming in. Okay, it looks like we have everyone on board now. So let's get the main presentation started. Once again, thank you for coming on board. Just to help you understand the interface here, we just got a quick slide to show you the webinar basics. This is the interface that you should see on your screen, or something very similar. The main section is obviously where the slides and polling will be. The question and answer box down in the bottom corner. Now, because it's such a large call, we don't actually have the phone lines open. So if you have any questions, enter them into the Q&A box down the bottom, and I'll either deal with them during the presentation, if it makes sense, or at certain points in the presentation, I'll also have a look at the question queue and see if we can answer those questions. Other parts of the environment is the speaker bio. You should see my bio up there in the top right-hand corner. Resources. We do have a couple of resources for this presentation. We have the Modbus map, the SIM 2251 Modbus map, and also a PDF of this presentation as well. And then there's media controls, although for this webinar we won't have any live media except for the volume. But if you're watching this on a recording, you will have you'll be able to fast forward and rewind. And that reminds me, this will be recorded and available for future viewing, just like the previous webcast that we held earlier in the year. So if you miss something, or you want to come back, or you want someone else to get the information, you can always go back to the recorded webinar. So let's get started. Oh, sorry, I forgot. You can also share on Twitter or Facebook or whatever your social platform of choice is. And if you wish to get a salesperson or a technical person to contact you about any of the information, you can also press that button there. So let's go through what we're going to talk about today. Communicating to your gas chromatograph through Modbus, RS-232, 485, or Ethernet. Basically, we're going to go through it step by step. The first step is look at the different options. What is the difference between serial, Ethernet? Actually, it says foundation field bus and heart here. We really won't cover foundation field bus or heart here. They're much more specific and detailed subjects in themselves. Just to say that they are available, or heart is not available on the gas chromatographs, but foundation field bus is. But we'll really be focusing on the serial and Ethernet today. The second section, we'll talk about the actual hardware connections, RS-232, 485, 422. Then we'll talk about Ethernet communications as well. Then we'll get into the Modbus communications, actually how Modbus works. We'll talk about the two different methods that we use, which is SIM2251 Modbus and then user Modbus as well. So that's the agenda for today. Just quickly having a look at the poll results, I asked everyone what's the main way you communicate to your GCs today. I know that if I asked this question 3-4 years ago, I would have seen all 485 and 232, but it's good to see that Ethernet, 34%, is definitely the most popular way to communicate to your GCs today. Ethernet provides a lot of advantages, which we'll talk about during the presentation, but that's interesting to see. It's good to see some people using fiber optic as well for long-distance communications, and it looks like we have 1 or 2 people that have foundation field bus. Like I said before, we won't really cover foundation field bus in this presentation. That will be something that we'll look into in a future webinar. So I guess the first question is to cover the basics and answer what is Modbus. Well, Modbus is a serial communications protocol. It's a way to communicate between industrial devices, and the way it works, it has a single host, and you can have 1 or more slave devices. So a host will go out and ask for information from a slave device, and the slave device will answer with the information that was requested. And in our situation, typically the master will be a flow computer, an RTU, a control system, DCS or PLC or SCADA system, and the slave device will be the gas chromatograph. Modbus was originally designed by Modicon, which is now Schneider Electric, back in 1979. It isn't actually a standard, but it's definitely the de facto standard. It's easily the most common way for serial communications in the industrial environment. And it's really ideal for gas chromatograph communications as it's widely available, very configurable, and very reliable once it's up and running. And that's where a lot of the problems come with Modbus serial communications, is getting it up and running. Commissioning serial communications can be very frustrating sometimes because you really need to make sure that everything is configured correctly for it to work. Once it's up and working, there's usually very little problems, but getting it up and working sometimes can be a very tedious and frustrating process. So let's have a look at the physical protocols. This is actually the physical wires, the actual physical connections that we use for serial communication. The first one we'll talk about will be RS-232. Now this is a 3-wire protocol. It's point-to-point, which means that it's only a single host and a single slave. This is not multi-dropped. You can't have multiple GCs on an RS-232 link. It's just 1 slave and 1 host, so it's a point-to-point communication. It's a relatively short distance communication. It's up to 15 meters or 50 feet, and it's good for local communication. So this is the kind of communication that you'll use inside a control room, inside an MCC, inside a local room communication where it's short distance and there's no need to worry about multi-dropped linking multiple devices on a single link. Then we have RS-422. That's a 4-wire communication. It's multi-drop, single master, but multiple slaves. So you can have 1 master talking to multiple GCs or multiple devices. Maybe you'll have a flow computer talking to a flow meter, to a gas chromatograph, to other analyzers, all on a single link. It's a long-distance communication protocol, so it's up to 1,200 meters or 4,000 feet. It's very robust. But it's typically not used, and the main reason is because 485 is a 2-wire communication protocol and is also very robust. It's long distance as well. Because it's only 2 wires, though, it's a lot cheaper to install. 4 wires is obviously twice as much as 2 wires, and so RS-485 has definitely become the standard for long distance serial communications. It's 2-wire, multi-drop, single master, multiple slaves, 1,200 meters or 4,000 feet, and it's definitely very common and very robust for industrial communications. Then we have Ethernet. Now, Ethernet, 5 years ago, I would have said that Ethernet was reasonably rare, but now we're seeing Ethernet all over the place. And I really like Ethernet. The reason I like Ethernet is very fast, it's very robust, and it's relatively cheap because Ethernet is everywhere now with your home systems and throughout the industrial environment, there's Ethernet everywhere. And so it's very cost effective to hook onto an Ethernet network. One of the really good advantages of Ethernet is that you can have multiple masters communicating over a single link to a slave. So I can have a flow computer, a Mon 2000 computer, I could have multiple flow computers, a SCADA system, all communicating to a single slave over a single link. So that's a really big advantage. It is relatively short distance though. It's only up to 100 meters or 320 feet. You can use repeaters and you can also use fiber optic to increase that distance. But it's definitely quickly becoming the preferred method. And as we saw in the poll before, it's definitely the preferred method with the people in the call today. So looking at the physical properties now, this is RS-232. So we have the master on the left and the slave on the right-hand side. And we have the connection. Now, it is a 3-wire communication protocol, and easily one of the biggest problems that happens with RS-232 wiring is that people wire the TX to the TX and the RX to the RX, which is actually wrong. You really need to cross it over because you need to connect the transmission, the TX from the master to the RX, the receiver on the slave, and the receiver on the master to the transmit on the slave. So that's definitely one of the most common wiring faults that we see. And in fact, when I'm doing phone support and people have serial communication problems, after checking that all their baud rates and all the other settings are correct, I say swap the wires and see how you go. And that very often fixes the problem. The other issue that we see with 232, it is 3-wire. The signal grounds must be connected. The signal that's on the transmit and receive lines is referenced to the ground, and so it's really important that you have that ground connection made so that the signal can pass through correctly and be referenced to a common ground. Another problem that we see, especially in very busy panels, is twisted pair, and shielded twisted pair is not used. Sometimes you can get away with just using straight wires, but when you've got motor drives and other serial communication happening in a single panel, it's really important to use shielded twisted pair cable so that you can become immune to any electromagnetic noise that may be occurring around the wiring. So shielded twisted pair cable will definitely make it a lot more reliable and get you up and running much faster. So let's move on to RS-422 wiring. This is sometimes called full duplex. It's a 4-wire protocol. And once again, the RX and TX, the receive and transmissions are swapped over so that the transmission on the master is connected to the receive of the slave, and the receive on the master is connected to the transmission on the slave. It's also very important to use shielded twisted pair cable. 422 wiring is used for long distance communications. You don't know what else could be in the conduit runs or in the cable runs with the serial communication, so it's really important to use shielded twisted pair cable. Now, sometimes you'll see a different way of marking the terminals. There's another way of marking the terminals. Instead of RX and TX, you can see A, B, Y, and Z. A is the receive on the master. B is the negative receive on the master. Y and Z is for the transmission lines. 422 is a multi-dropped protocol, so you can connect multiple devices to this link, and all those multiple slave devices are connected in parallel. So that's RS-422 wiring. Let's move to RS-485 wiring now, and this is called half duplex, and it's preferred because it's only 2 wires. And once again, you see that the wires are swapped over so that we have the transmit of the master is connected to the receive on the slave, and the receive on the master is connected to the transmit on the slave. Shielded cable as well. Now, sometimes what you can do is you can change a full duplex into a half duplex by connecting the pluses together and the minuses together of the RX and the TX. And so you can convert a full duplex into half duplex so that you can save those wirings. And in older systems, you'll see that you might have to do that wiring manually. On many new hosts and other systems, you'll see that that's done automatically. Once again, 485 wiring is multi-dropped as well. So you can connect, theoretically you could connect up to 254 slave devices, but in reality you wouldn't really want to go more than 10 devices just because of the amount of information that's traveling over those lines and looking at the lag time between getting communication to the individual devices. Now, one thing that I don't see very often, but is important for people that are out in the field, is that when you have particularly long distance cables, sometimes you may get reflections occurring on the cables, which is causing intermittent faults or intermittent communication issues. One way you can fix that is by putting on 120 ohm resistors on the 2 endpoints of the wiring. So if you have multiple multi-drop slave devices, you don't want to put 120 ohms on each of the devices. You only put 120 ohm resistor on the master and the very furthest slave, and that will stop any reflections causing intermittent communication issues. You definitely don't need that on every single installation. I would say that the majority of 485 communications out there do not have terminating resistors, but if you're finding that you're having intermittent issues with the communication on a 485 link, then adding these terminating resistors can definitely help you out. Now we'll have a look at Ethernet wiring. Ethernet is just standard Ethernet wiring, and you'll see this in many places. You can find out where Ethernet wiring is. On an RJ45 connector, the transmits are on the first and second terminals, and the receives are on the 3 and 6. You do need to cross the wires, cross them, the RX and the TX over, although most host devices, most modern host devices can automatically detect that and automatically correct for crossover. So that's not generally an issue in today's modern Ethernet communications. It still should be twisted, shielded pair cable to provide immunity to noise and crosstalk, and definitely, sorry, I'll move back there. Ethernet is definitely one of the most common ways we see it communicating now. Now, what I'm going to do is just quickly have a look at some of the questions that have come in before I move into the next section. Okay, here's a good point. Actually, someone has mentioned that sometimes with really long cables, you can put a 0.1 microfarad capacitor between the shield and the ground. That can help. I find that the terminating resistors often can really help, but if you have a very, very noisy environment with lots of motors around, variable speed drives especially, then a capacitor can help as well. I've got a question about the Modbus mapping. We will cover that, especially we'll use talk about custom Modbus maps right at the end of the presentation. So you'll have to wait until the very end section, but we'll definitely cover that. And I've got a question about HART. We don't really cover HART communications in this presentation, mainly because HART is a very slow protocol. It's also really designed for 4 process variables. You'll see that there's the main process variable and 3 other secondary variables. In a GC, we have a lot of floating points that we need to communicate with. We have typically up to 12 to 16 components that we pass along the actual concentration with. We have calculations, we have response factors, we have a lot of information, and the HART signal, it just doesn't provide enough bandwidth to send that information, and so there really is no GC out there that uses HART as a communication protocol. Okay, so now I'm going to move on to the next section, which is where we get into the serial communication settings. And it's really important that you use the exact same communication settings for the host and the slave. Now, here we're showing the Mon 2000 for the Model 500 and Model 700 GCs on the left-hand side, and the Mon 2020 menu for the XA series of GCs. To go to the communication settings on the Mon 2000, you go to the serial ports, and on the Mon 2020, you go to the communication settings. And this is where we'll set up the serial communication settings. Now, before we get into the actual settings, there's 2 major formats that we use for communicating over serial links. There's ASCII, which was the original format, which transmits characters in 7-bit ASCII characters, so it's 0 to 9, A to F. Then we have and ASCII uses an error check because it's got 7 data bits. It uses a parity bit at the end to do an odd-even error check. It uses 1 start bit, 7 start data bits, odd or even parity, and we can have 1 or 2 stop bits to say this is the end of the message. That's the ASCII format. The RTU format transmits a full 8-bit binary number from 0 to 255. The error check is actually a CRC check, which is a checksum, which is transmitted at the end of the message packet. It uses 1 start bit, 8 data bits. It doesn't use parity because it uses the CRC error checking, and you can have 1 or 2 stop bits. And without a doubt, RTU is definitely the most common method used for communication today. Some older systems will still use the ASCII format. All of our gas chromatographs can communicate with ASCII and RTU, but RTU is definitely the most common format used. So looking at how we set this up inside the GCs, on the left-hand side we have the Mon 2000, the old Model 500, Model 700 configurations, and on the right-hand side we have the screen from the Mon 2020. The first thing we're going to talk about is baud rate. That's the speed of communication. That's how fast in bits per second that we transmit data. You can select anywhere from 300 up to 115,200. The higher the baud rate, the greater the susceptibility to noise. So while it's great to have really fast communication, it's not that much useful if you're getting a lot of errors. And so it's really important that you use a baud rate which is fast enough to get you the information quickly, but not too fast so you get a lot of errors. And so the most common that we see is 9600 or 9200. 9600 we used a lot in the old Model 500s, but now we've moved up to the default being 192. And there's really no advantage to using much faster because with a gas chromatograph, typically the analysis cycle times can be anything from a minute to 15 minutes, and the delay in slower baud rate really doesn't affect the speed of getting information from the analysis because of the cycle time of the GC is much longer than the issues with communication. So the next part we're going to talk about is the protocol. That's what we were talking about before, the RTU or ASCII. Older GCs on the Model 500 and the Model 700, you'll see that the protocol, we have to select that. On the more modern GCs, the XA series of GCs, that's automatically selected, so you don't have to make a selection, but you will need to select that on your host device. The next part is the serial port settings, which is a data bit, stop bits, and parity. We kind of talked about that before with the ASCII and RTUs. You need to make sure that these settings are exactly the same as what's on your host device. So with an RTU setup, you'll set it up with 8 data bits, 1 stop bit, and no parity. And with ASCII communications, you'll be setting it up with 7 data bits, 1 stop bit, and even or odd parity. And it's really important to make sure that you have that parity set correctly and matched with the host device so that you can get good communication. The next setting we see is hardware flow control, the RTS or CTS, a request to send or clear to send. That's available for RS-232 communications, where you can have flow control so that you don't get collisions on the network. But to be honest, in the industrial environment, it is very rarely used because people just like to connect 3 wires instead of 5 wires, and so it's available, but it's not really used in the industrial environment. Now, the Modbus ID, the COM ID, as it's called on the Mon 2000, the Model 500, Model 700, or the Modbus ID, this is really important for communicating when you have multi-dropped networks. Now, the default is set to 1. On the Model 500 and the Model 700, if the COM ID is set to 0, then the Modbus ID is actually defined by some jumper settings, which you can find about how to set up in the manual. So if it's set to 0, it'll use the hardware default setting by the jumpers. On the XA series, it's all set up with software, and by default they're set to 1. But it's really important if you have a multi-drops installation where you have multiple GCs or multiple devices on a single link, it's really important that each of those slave devices has a different Modbus ID. And the host device must be configured so that when it's trying to communicate to the GC, it's using the correct Modbus ID that's been assigned to it. So I've seen that happen before. You connect up 3 GCs on the same network. They don't go in and change the Modbus IDs, and so the host says, hey, I want to get information from GC1. Well, because all 3 of those slave devices are set up with the same Modbus ID, they all go to answer at the same time. You get a lot of noise on the network. It's very intermittent, and it can cause, it will cause errors in communication. So it's important for multi-dropped links that you change those Modbus IDs so that they're unique for each slave device. But for point-to-point, you would leave it at the default of 1. Now, Ethernet TCP/IP, as we saw in the poll earlier before, we see that there is a big move towards Ethernet communications. And the biggest advantage of Ethernet is that it allows us to have these virtual ports. So even though the flow computer is talking to the GC point-to-point, and the Mon 2020 in this case is talking to the GC point-to-point, the software inside the GC will recognize that they're coming from 2 different devices and will set up a virtual port on the fly inside the GC so that we can have multiple masters talking to the one GC over a single Ethernet link. Now, in theory, we can have up to 16 different virtual ports, but in reality, getting up to more than 8 devices talking to one GC over one Ethernet link can start to become problematic with collisions on the network. So But it is really good that you can connect multiple hosts up to a single slave through a single Ethernet connection. That's a really good advantage of Ethernet TCP/IP. And the other advantage is that you can communicate with the flow computer or the DCS or RTU or SCADA system, PLC, to the device, and you can also, on the same Ethernet link, talk to the GC with the MON 2020 or the MON 2000 diagnostic software without interrupting the communications to the host devices. So you can talk to the GC, diagnose it over the same Ethernet link without worrying about the connections to the flow computers or the SCADA system or the DCS system. So that's a really big advantage of using Ethernet TCP/IP. And all of our XA series GCs actually have 2 Ethernet ports. So that you can keep your control network separate from your diagnostic network if you need that in your particular installation. Now, looking at Ethernet settings, you can just Google Ethernet settings and you'll get a million pages that tell you how to set up an Ethernet setting, Ethernet network. But just quickly, the settings must be configured for each individual network. The GCs go out of the factory with default values, but they will not typically be the values that you'll have in your installation. So you do need to configure the Ethernet settings for your installation. The IP address is the individual address of the device. So every device on that network needs a unique IP address. The subnet mask is the mask that defines the range of addresses on that subnet. So that's the range of devices that allow it to, that the GC will communicate to with the IP settings, and we'll talk about that on the next slide a little bit. And then the gateway address. If you have a connection to a firewall, to a larger wide area network, then you would put that gateway address for that gateway to that wider network. That will go in the gateway setting, although in most installations we don't see that. So I'll go back. All Modbus traffic will occur over the port 502. This is the virtual port 502. If you have a firewall system, it's really important that they open up your IT or whoever looks after your network can open up these ports. And also the MON 2020 software uses ports 10,000 to 13,000 to communicate to the GC and do diagnostics. And we have had problems where the firewalls have been set up to block these ports. Firewalls are often set up to block a whole lot of ports to stop people from trying to break into networks. But it's really important that if you want to communicate with the MON 2020 software to an XAGC, the ports 10,000 to 13,000 need to be opened up on any firewalls that you have. That firewall could be on your computer, it could be on the routers, it could be on the modems that are connected, but those ports need to be opened up. So just a quick overview here of what a network looks like. You can see here that I've given each device an IP address. They all have the same subnet mask and they all have the same gateway. You'll see there that the computer, the rock on the bottom left-hand corner, and the GC, they all have an IP addresses that start with 10, 10, 10, and then the last number is different. That's their unique IP address. You'll notice that flow bus up on the top right-hand corner, it has an IP address of 1010.205.103. That will not be able to connect on this network because that subnet mask there shows 255-255.255.0. That means that where those 255s are, that means that those components of the IP address need to be identical to allow communication. And in this case, that flow bus up in the top right-hand corner, the third IP number is not the same as the rest of the network, so it will not communicate. And so if we change that IP address to be 10.10.10.103, it will now communicate over this network, and it will now be able to communicate over to the GC. So that's an important fundamental for TCP IP networks, is that the IP addresses, while they need to be unique, they need to be in the same subnet range, and that is set by the subnet mask and the numbers in the IP address, the first three numbers in the IP address. Okay, so now we're going to move on to Modbus maps. I'm just going to quickly have a look before we move on to this. I'm just going to have a look at some questions here. Here's a good question, actually. Can anything be done so more than one person can log on through the Ethernet? And I believe what you're talking about there is where you're talking about, let me go back to this picture. If we had multiple computers here that had Mon 2020 running, can we have 2 or 3 people talking to the GC with the one Mon 2020 link? We've actually decided not to allow that, and the fundamental reason for that is that if there's one person connected to it and they make a change and someone else is connected to that GC at the same time, they may make that change back. They may reverse that change not knowing that another person is connected. So at the moment, we don't allow multiple sessions of Mon 2020 to a device, to a GC, simply so that we don't get into a situation where one person is changing something and another person tries to change it back. So that, although you can have multiple computers all over the network that could talk to the GC with Mon 2020, only one person can be logged on to make changes at a time. I've got a point here. Someone's highlighted that with a 485 bus, that it should be daisy chained. That's correct. They should all be connected in parallel. You can't do a star network where they all come out from from the host. You really need to daisy chain them along because otherwise a star network will cause you lots of communication issues. Okay. I think there's a question here about sockets on the Ethernet port. We recommend to use only up to 8 connections. That's the virtual ports or sockets on the Ethernet port. You can do more, but we do see people having communication issues. Do we have any other options if we cannot use a 502 port? Actually, no. Modbus, the relative standard of Modbus, although I'm hesitant to use the terminology standard, but the protocol for using Ethernet Modbus is to always use port 502, and the GCs don't have the option of changing that port at this moment. Can we have wireless connectivity using Ethernet TCP/IP? Yes, certainly. With now, we don't have wireless inside the GC itself, but you could definitely hook up the GC to a wireless hub and be able to communicate to the GC wirelessly. And in fact, we do that in the factory here, where we have a wireless network and we can talk to the GCs over the wireless network. We don't have the wireless adapter inside the GC itself, simply because there's a lot of options out there for wireless connectivity, and there's also a lot of issues with having a wireless hub inside a explosion-proof enclosure. And to be honest, because of security concerns, there's not that much call for wireless networks in the industrial environment, although that is changing, but it is a standard wireless Ethernet. It's exactly the same as your Wi-Fi that you might have in the office or at home, so you would be using off-the-shelf components for that. I got a question here. Does the GC also have a MAC address? All Ethernet devices have a MAC address, but that is not something that we use in communications, in typical Ethernet communications. It's not something that we configure, and it's not something that we actually use. Okay, I'm going to move on, and there's also some other questions there, but I think I'll cover most of them in my upcoming slides. Oh, here's a good question, though. Can I use RS-232, 485, and Ethernet at the same time? Yes, you can. We have multiple serial ports. On the 700XA, we have up to 8 serial ports with expansion ports as well, expansion cards. On the Model 500, we have up to 8 serial ports. They can be a mixture of 232 or 485. The 370XA has 2 serial ports, which can also be 232 or 485, and the Ethernet is separate as well. So you can have one device talking to a GC with 232, another device talking with 485, and another device or many devices talking over the Ethernet protocol. So there's no problems, and they're all separate. They're all unique Modbus maps, and so you can actually have one serial port set up for one Modbus map, the other serial port set up for a completely different Modbus map, and the Ethernet set up with a different Modbus map as well. A question here, are all Ethernet and serial settings retained in a power loss event? Yeah, definitely. Everything is stored in non-volatile memory because we know power gets switched off on these GCs, and so we definitely don't want you having to go back and reconfigure the unit once the power has been taken off. I got a good question here about OPC. You can use OPC, but what we tend to do with OPC is we'll have an OPC server sitting on a computer, a standalone server, or on a customer-supplied server. The OPC server will talk to the GC using Ethernet Modbus, and then the actual OPC communication occurs between the server and the host device. Okay, so let's move on to Modbus communications. I'm just looking at the time here. We're up to 42 minutes already. So let's talk about Modbus communications. Modbus communications relies on Modbus maps. These are configured maps that are configured in the slave device, and the same Modbus map needs to be configured in the host device, because this is the mapping of where the information resides. So each data value from the GC has a unique register where the value can be then accessed by the host. The original Modbus protocol, it comes from 1979. It did not support floating point numbers, and that's actually caused a problem because now there's multiple ways of putting floating point numbers on the Modbus link, and in fact the GCs that we have 2 different ways of putting up floating points up on the Modbus communication links, and so that's one of the differences that we see between different devices. So the 2 different message formats that we use are SIM2251 and user Modbus. Now SIM2251 is commonly used for the natural gas custody transfer type applications with flow computers, RTUs, or SCADA systems. It's a modified Modbus protocol that allows for floating point numbers to be transmitted over the Modbus link. And the big difference is that it uses a single register per floating point. On older GCs, the Modbus map, well, on all GCs, the Modbus map is predefined. So a SIM2251 Modbus map always looks the same. The advantage of that is a lot of flow computers and RTUs and SCADA systems have this pre-configured, all ready to go, and so there's very little editing required, or usually no editing required by the end user or setup for the Modbus map. Now, on the XA series of GCs, you can edit that Modbus map, so you can add things or take things away from that Modbus map if you want. And you may have heard this, and you may see this in flow computers and RTUs and SCADA systems be referred to as the Daniel or Enron Modbus format, coming from the old Daniel days of when when the Daniel Gas Chromatographs developed this with the Enron company. So that's the common way you may see it referred to. And then what we have in our GCs is what we call, and each 32-bit floating point is assigned a single register. So that means that every floating point has one register, so we have a 7001, 7002, 7003. Even though they're 32 bits, they each take up only one register. And that's significantly different to what we call user Modbus. And user Modbus is what we commonly use for DCS systems, PLC systems. Most control systems use what we call user Modbus or a Modicon Gould format. The coils are predefined. That's where all our alarms and digital inputs and outputs are defined on the Modbus map. But the numeric registers are user-defined. So these need to be set up. Now, we do use a default map in the factory, but it's a user-defined map, and it's fully configured. So this means that there is no pre-configured map that you'll have in your DCS system. You'll have to configure this as a part of the configuration. One of the major differences of this kind of Modbus is that the 32-bit floating points are each actually sent as two registers. And in our case, we send the least significant byte first. So that means that they'll appear at registers like 1001, then 1003, then 1005. So if you tried to look for register 1002, you'd get an error back because that's actually the second half of the floating point. So that's a big difference between SIM2251 and user Modbus map. So looking at the SIM2251 registers, it's a predefined map. So this is where all of this is predefined, and it's set up in many flow computers and RTUs and other GCs, and even our competition have flattered us by copying exactly what our Modbus map is. So to start off with, we use component codes to identify what components are being measured. And just to show you what the component codes are, if I look at Mon 2020 and go to our component data table here, and then click on what we call the standard values, you can see here on the far right side, if I slide across to the far right side, there's the component codes and component indexes there. So each component has a unique code. And just to make it easy for you for reference, the component codes here, they're listed from 0 to 255. So each of the common components that we measure have their own code. And so if we look at the Modbus map and we were to look at register 3001, we would see that it would have a component code that matches that component that's going to appear in the analysis results. And this is how we allow the flow computers or SCADA systems or host devices to recognize where the information resides that they're looking for. The next set of registers we're going to look at is a 3033 to 3045. This is the stuff that's the information about the time and date of the current time and date, and also the last analysis start time and date. Then we have the alarm registers. The 3046 to 3057 is where the alarm registers are. I'm going to go through this pretty quickly because we do have a PDF that of this presentation, so you can refer to this at a later date. But essentially what we've done with these alarms is that for each 16-bit byte register, we have these individual alarms put up there for you to read. The way this works is that okay, hang on, someone telling me that I've got some problems with my slides here. Hang on. So we have the alarm bitmaps here. Now, that means that if the analog, say the analog input 1 was low, then bit 2, whoops, what's going on here? There we go. Bit 2 would be set to a 1. Now, the way this can work in reality is you could actually map each individual bit, or you could look to see that if register 3046 was not 0, then there's an alarm. Or if 3046 is equal to 0, then all of the bits are set to 0, and so there's no alarm and life is good. So that's how we use the bit maps. I won't go through in detail with all the individual alarms in there, but just remember that we do have that resource available later. You can download this presentation as a PDF. Now we're having a look at the last two registers, the 3058 and 3059, the new data flag and the analysis calibration flag. So the new data flag is set to a 1 at the end of the analysis cycle, and what will happen is the host system will read the information. Once it's read all of the analysis data, it then actually writes back a 0 to the 3058 data flag to say, I've read the information and we're good to go. So, and then when the next analysis cycle is finished, the GC will reset that to a 1 to say my analysis cycle is finished. The master device will look at that change, say, okay, I've got new data now. Now I'll go and read all that information on the analysis cycle. And then the analysis calibration flag, if it's an analysis run, it will show a 0, and a calibration cycle will show a 1. Now we're going to move to the floating point registers here. So 7001 to 7016 contain the floating point values of the last analysis, and the order that the analysis is put into the Modbus map is the order of the components actually go past the detector, and that's the order that they appear in the component data table. So in this case here, on the bottom right hand side, you can see in that component data table, propane is first. So in 7001, we'd see the analysis results for propane, then 7002 we'd see ibutane, then N-butane, and so on through the component data table. And notice there that the floating points are at each register, so 7001, 7002, 7003, which is different to the Gould Modbus where it would be 7001, 7003. So now sometimes one of the issues with the 7001 to 7016 registers is that if you have multiple streams, it'll update with the different streams, and so we have made available the individual streams on different registers of 7621 to 7766 is the results for each of the individual streams. Now, to look at these Modbus maps, sometimes different GCs will have different Modbus maps configured in there depending on who's bought the GC and the system that it's being connected to. To look to see what your Modbus map is, on Mon 2000 you go to PC Config Report on the File menu. Then you have this selection here. You check the communication box down near the bottom. You decide where you want the output to go to. So you can save it as a text file, or you can save it to the screen, and then press the Start button, and you'll get a report showing you what the Modbus information, what the Modbus map is. On the Mon 2020 software, it's under Logs and Reports, GC Config Report. And then we have once again, you go down to the communication, select that, the output file or screen, press start, and that will give you the communication settings for all of the ports and the Modbus maps that are being configured. Now we'll move on to user Modbus. User Modbus is fully configurable. It uses the standard Modicon formats. We do pre-map the coils 0 to 150 with the alarms and status values, and we typically use registers 1001 and above for floating point values for the analysis results. Now, here's one of the problems that happens with Modbus. It isn't a standard. It's been built up as a de facto standard, and so there's some confusion and some different ways of setting up the Modbus maps. And what we find is that even though we set up the GC address as 1001, a lot of host devices actually incorporate the function code. And you see there on the right-hand side, there's the function code. So like to read a input register or read a holding register, an input register is function code 4. It will combine the address with the function code, so you'll actually configure the DCS to read 4000, 1000, and 2. That's the other issue that we see with communication with host devices and slave devices, as that often the host device will have an offset of 1. And to be honest, I don't know why this is. It causes a lot of confusion. I wish everyone would just get on the same page, but unfortunately, this is the way that we see many systems are set up, so that if the GC address is set up to 1001, the DCS reference will actually be 41,002. And also remember, now we're looking at floating points in the Gould format. So each floating point takes 2 registers, and so the next register on the GC is 1003. On the DCS or PLC, it'll be 41004, and 1005 will be 41006. And this is not just something that's unique to GCs. A lot of slave devices, in fact, most slave devices are configured this way, with the DCS or PLC having to be configured with the function code and the offset in there as well. We do see a little bit of changes with some more modern devices, but this is one of those frustrations of working with Modbus communication. Once it's up and running, once it's configured, everything is great. It's just knowing about these little idiosyncrasies of Modbus communication can really get you out of a pickle very often. So just remember that the DCS or PLCs have the function code first, and also often there is an offset of 1. So now I'm going to look at how we configure that up, a user Modbus. So on Mon 2000, we'll go to serial ports, and we'll select registers. And this will allow us to bring up the user Modbus interface. And on the user Modbus interface, you can see here, it's starting off blank, completely blank. And so we'll enter the register number we want. We'll choose the value that we want to put on the Modbus map. And here I've picked up the C6 Plus component. And one of the cool things that we have with our Modbus map configuration is that instead of you having to do those steps for every single component, we have this copy C Plus or copy and increment component. And so if you just press that button, it will automatically increment the registers, increment the components, and now it's looking at the second component, the third component, and so on. So now I've got all of those components that have been measured, and once I've done that, I can then press the copy and increment stream button, and that will allow us to move to the second stream. It actually copies the ethane across, so you would choose the first component again, and then do the copy increment component again to get the full Modbus map. It's important that when we, I'll go back. So once you've saved this, you click on OK and it saves it. Then you need to change the port usage to now use that user Modbus so that it's using the Modbus map that you configured. Now on Mon 2020, it's very similar. The menu you go to is communication. Then you click on the registers button. It'll open up. Now the Modbus map is a little bit better, a little bit different on the Mon 2020. So we would create a new one. You give it a file name. You select user Modbus as the register type. And now you pretty much add the values like we did with the Mon 2000. So we choose a float type. We'll choose the component. And the component copy and increment for components and copy and increment for stream buttons are there on this Modbus map editor as well. And so you can go through and fully configure up your Modbus map. And it's not just the component values, the analysis values that are available. There's also, you can look at response factors. You can look at carrier gas pressure on the 370XA. You can look at a whole lot of heater values. You can look at calculated values. You can put pretty much any float, any data point that's inside the GC, you can put on a user Modbus. So you would save that Modbus map, and then once again, when we go back to the communication setting, you'll update the map file to use that new user Modbus map. So that's it so far for the for our main part of the presentation. I've just hit exactly an hour. So now I'll open it up to questions. So let me have a look at our question panel and see what questions we have. I need to make my panel a little bit bigger. Come on, there we go. So, okay, yes, I've got a question. Was that the custom Modbus mapping? Yes, the user Modbus is the custom Modbus mapping. You can actually modify the SIM 2251 Modbus maps in the XA series GCs as well. So you can customize that Modbus map, but in the fully configurable Modbus map would be the user Modbus map. I've got a question. Is it the only available protocol for the GC? There is a Foundation Field Bus protocol that's available as well. We haven't covered it in this presentation because that's really a subject all by itself, and it's not as common as what we've seen before, as with serial communications and Ethernet communications. So Foundation Field Bus is available. We've looked at other protocols. We're always considering other protocols, but at the moment we're staying with Modbus and Foundation Field Bus because they really suit the needs of a gas chromatograph. And it's important to remember when we talk about serial communications to a GC, there is a lot of information that we look at. There's up to 16 different components. There's calculated values. There's alarms. There's diagnostic values such as response factors and retention times that we can look at. There is a lot of information, and a lot of the protocols that we see don't really allow for a lot of information like that to be sent over, like Profibus and some of the other field bus protocols. So that's a very big limitation, but we are always looking around and seeing where the world is moving as far as communication goes. There actually is an Ethernet protocol that is becoming more and more popular that we've got some interest in, and actually I would be interested to know if you can put in your question and answer box if you're interested in the Ethernet TCP/IP protocol, which is different than Modbus. If you are interested, you know what that is, and you're interested to see that in a GC, I would be interested for you to just put that into the Q&A and send us a note about that so that we can track that information ourselves. If I need to read the data from the GC in two PLCs at the same time, is it possible to do that? Yes, it definitely is. It's possible to do that using either unique serial ports, so you can have multiple serial ports. So one PLC talks to one serial port, the other PLC talks to the other serial port, or you can have both of the PLCs talking over the Ethernet link at the same time as well. And that's definitely possible, although if they're talking over the same Ethernet link, they do need to use the same Modbus map. If we forget the GC IP address, how can we recover? You'll have to physically go to the GC and communicate to it. If you hook up the Mon 2020 to the local Ethernet port and turn on the DHCP server, then the default Modbus address will now be used for that RJ45 connector. More details about that are in the manual, but if you forget the IP address, you can go locally to the GC with Mon 2020, connect to the local port using the DHCP server. There's a little switch inside the electronics that turns on the DHCP server, and you'll be able to use the default IP address that comes configured with Mon 2020 to communicate to the device. There's no way to get that IP address remotely, and that's a security concern as well. Does the SIM2251 map have all the data points in the GC available? Use a Modbus map only for custom configurations. You can actually use SIM2251 for configurations, custom configurations as well. So if it's a process GC that's being used for, say, a depropanizer or an ethylene circuit or something like that, you can still use the SIM2251 Modbus map, and all of the information will be available there. But the chances that your DCS or PLC or SCADA system will be able to talk SIM2251 is kind of remote. So that's where we'll use the user Modbus map, because that tends to be the most common method of communicating to those kinds of host systems. Not all of the data points are available on the SIM2251 Modbus map. In the Model 500 and the Model 700 GCs, the older GCs, the Modbus map for SIM2251 is fixed, but on the XA series, you can modify that Modbus map, and then you can add whatever data points that you may be interested in putting in there. Can the user Modbus map be saved and downloaded to another comparable controller? Yes. You can take a Modbus map that's been configured on one GC and download it or upload it, depending on how you speak, to another GC. You would want to check that all the connections are correct, but the data points will still be in the second GC, and so yeah, it will transfer. And actually, that's what we do at the factory, is we have a default Modbus map that we use for custom GCs, and we upload that into the GCs during the checkout process. Okay, so I think that's all of the questions that I have there. With the questions, I've gone a little bit over our hour time. But I think we've covered this, a pretty large subject, and we could definitely go on for longer to talk about serial communications. But I think this is where we'll close it now. So thank you very much for your time. I hope you found this useful. I will put in a plug for the other webinars. We did do a webinar on validating the operation of a GC. That is available for on-demand now. You can get that at the same place that you registered for this course, and this presentation, and will also go out as a link in an email. later on today or tomorrow. We also have 3 more webcasts coming up. June 16 is installation considerations for GCs. August 11 is maintaining your GC at optimal performance levels. And then October 20 is a sample handling system. So once again, thank you very much for your time. We do have a poll at the end here just to tell us, just rate us how you think we've done with the webcast. And once again, I've got to say thank you very much for your time, and I hope you found this to be informative and useful for you. Thank you very much. Bye-bye.